We were looking at the examples of second order elliptic operators, and we were looking at Dirichlet problems. That means on the boundary the function is prescribed. Now we want to look at what is called the Neumann problem. So omega in Rn bounded open set and gamma equals d omega. So if u is a smooth function defined on omega, then we denote by du by d nu equals outer normal derivative. Which is equal to grad u dot nu, where grad ux of course is the gradient, so du by dx1 du by dxn, and this is on gamma, and nu equals nu1 nu n. This is the unit outer normal on gamma. So you have the domain, it will depend on x of course, so at each point you have a tangent and then you have the unit outer normal, which is like that. So this is again dependent on x, okay, nu equals nu of x. Okay, so now we want to look at the following problem. So consider minus Laplacian u plus u equals f in omega and du by d nu equal to 0 on gamma. So this is the Neumann problem, we will call it n. Okay. So if u is smooth enough, and then so which will imply that u is in h1 of omega and f in L2 of omega. Okay, and so if you multiply by then by Grimm's theorem, for every v in h1 of omega we have the following. So integral minus Laplacian u on omega into v plus integral on omega uv equals integral omega fv. So if you integrate the first term by means of Green's formula, you will have grad u dot grad v dx plus, or rather minus integral on gamma du by d nu times v and then d sigma plus integral over omega uv dx equals integral on omega fv dx, and then du by d nu equal to 0, and therefore this integral on gamma goes to 0. So we have, if f belongs to L2 of omega, then weak formulation of n, this is nothing but integral omega, find u in h1 of omega such that grad u dot grad v dx plus integral on omega uv dx equals integral on omega fv dx for every v in h1 of omega. This is called the weak formulation of the Neumann problem. Okay, so of course if you have classical or smooth solution of n implies weak solution, as we have just seen. So weak formulation here, therefore the basic space is h1 of omega, and then the linear form is integral omega fv dx, and the bilinear form is integral grad u grad v plus integral uv, which is nothing but the inner product in h1 of omega, and therefore by Lax Milgram there exists unique weak solution. That's immediate because you just have the inner product here, so that is definitely elliptic. So we have nothing to prove. So on the other hand, if U is a weak solution, taking V equal to phi in d omega implies minus Laplacian U plus U equals F in the sense of distributions. So as distributions, you will have that this is certainly true. So now let us assume weak solution U belongs to H2 of omega intersection H1 of omega. So let us assume that you have some additional smoothness, which again, as I have repeatedly said, is by means of a regularity theorem, and generally for reasonable domains this will always be true, and therefore we will see this. Okay, so now from we get by going back, retracing the integration by parts formula. So star implies minus Laplacian U times V because, so here this means that Laplacian of U belongs to L2. Anyway, it's in the sense of distributions, and anyway you have this. Okay, minus Laplacian U V integral omega plus integral du by d nu V d sigma on gamma plus integral on omega uv dx equals integral on omega fv dx. So now we take V in so we take V in d of omega. Then of course this term will vanish, so this will imply that minus integral omega, minus Laplacian U plus U minus F times V dx equal to 0. Now we know that minus Laplacian U, U, F are all in L2 of omega, and you have d omega dense in L2 of omega. So this implies that minus Laplacian U plus U equal to F in L2 of omega. So as function of L2 of omega, this is true. So now if you go back to star, so call this double star, then double star implies that integral omega minus Laplacian U plus U minus F into V dx plus integral on gamma du by d nu V d sigma equal to 0 for every V in H1 of omega. But then minus Laplacian U plus U minus F is a L2 function which is 0, so equal to 0, and therefore this implies that integral on gamma du by d nu times V d sigma equal to 0. Okay. Now H1 of omega gamma naught into H half of gamma is on 2, and H half of gamma is dense in L2 of omega. Therefore, this shows that so call this dagger. So dagger true for all V in H half of gamma, because of this ontoness of gamma naught, and therefore you have, this implies that du by d nu equal to 0 in L2 of gamma. So we show that if u is in H2, this satisfies the boundary condition. Okay, so now we want to make a remark. So there is a difference between the Dirichlet and the Neumann problems. In Dirichlet problem, the boundary condition was included in the space concerned, space where we look for a solution. So we worked in H10, or we worked with the translate of H10 by means of a lift of the boundary condition, so that all functions where we are looking for a solution will automatically satisfy the boundary condition. In the Neumann problem, boundary condition came as a natural consequence of the weak formulation. Okay, so this is why we call Dirichlet condition is an essential boundary condition and the Neumann condition is a natural boundary condition. So now let us look at the inhomogeneous problem. Minus Laplace in u plus u equals f in omega, and du by d nu equal to g on d omega gamma. Okay, so now we assume that f is in L2 of omega and g is in L2 of gamma. Then again, if you multiply by means of v and write it, so you will get integral grad u grad v on omega minus integral on gamma du by d nu into v, and then plus integral on omega uv equals integral on omega fv. So if you now put in the condition du by d nu equal to g on gamma, therefore you will get the weak formulation find u in h1 of omega such that for every v in h1 of omega we have integral on omega grad u dot grad v dx plus integral on omega uv dx is equal to integral on omega fv dx plus integral on gamma gv d sigma. Okay, so this is the thing, and the right hand side mod fv is less than equal to mod f 0 omega mod v 0 omega, which is less than equal to mod f 0 omega norm v 1 omega, and integral on gamma gv is less than equal to mod g 0 gamma mod v 0 gamma, but we know this is less than equal to, because v is a trace operator, therefore mod g 0 gamma c times norm v 1 omega. Okay, we are just having, so by the trace theorem, and therefore you have that the right hand side is a continuously, so we have the basic space is h1 of omega, the linear form is fv dx plus gv d sigma, and then the bilinear form is grad u integral grad u grad v plus integral uv, and that is again the inner product, and therefore it is h1 elliptic, and consequently Lax-Milgram implies there exists a unique weak solution. So again, if u is in h2 of omega intersection h1 of omega, then gamma 1 of u belongs to L2 of gamma, and you will have gamma 1 of u equals g, and this of course is nothing but du by d nu. By the Green's formula you can just exactly as we said, and we also have that the weak solution satisfies differential equation in the sense of distributions, and of course if u is in h2, minus Laplacian u plus u equals f as L2 functions, and therefore you will get that gamma 1 of u equals g. Okay, so this will everything will come exactly as we have seen before, and therefore, and this will imply also that g belongs to h half of gamma in this case. Okay, so necessarily it will be, unless it's in h half of gamma, you cannot expect that u will be in h2 of omega. Okay. Okay, so up to now there was a difference between the Dirichlet and Neumann problems we had, other than the imposition of the boundary condition, namely that in the Dirichlet case we looked at minus Laplacian u equals f and u equals 0 on the boundary or g on the boundary, and here I always seem to put minus Laplacian u plus u equals f, okay, because I wanted ellipticity in the h1 of omega norm, and since we do not have Poincare inequality for h1 of omega in a bounded domain, we had to put this extra term. So now what happens if I don't have that extra term? So if I have minus Laplacian u equals f in omega and u du by d nu equals g on gamma, okay, then the weak formulation will be u in h1 of omega such that, again you multiply, integrate by parts and write everything, will be grad u dot grad nu dx equals integral on omega f v grad nu grad v, sorry, f v dx plus integral on gamma gv d sigma for every v in h1 of omega. Okay, so now if I take omega is bounded, so v identically 1, v belongs to h1 of omega, then if I substitute, this will imply that 0 equals integral of f dx plus integral g on gamma g d sigma. Okay, so this is a necessary condition for the existence of a solution. So there is a compatibility condition, this is called a compatibility condition. Now if you write it out in the functional analytic framework using the operator capital G, which maps the function to the f to data to the solution and so on, then there is we can get a compact operator by Relic's theorem, as we have done before in the general second order elliptic Dirichlet case, and one can prove by Fredholm alternative implies that this is also sufficient. So this is a necessary and sufficient condition for the existence of a solution, which comes from the Fredholm alternative. Now this is because if you look at the Laplacian u equal to 0 in omega and du by d nu equal to 0 on gamma, the homogeneous problem, then this will mean that u is a constant. One can prove if omega is connected, of course. Okay, and what is the Fredholm alternative? If you want to have a solution for the inhomogeneous equation, we have already seen, you can show that this map is the map with G star which is associated with this will be the same as G, namely it is self-adjoint, and therefore it should be orthogonal to the kernel of this kernel, and that means there exists solution if and only if f and g belong are orthogonal to the function v equal to 1, and that is precisely this condition which we have put here. So by the Fredholm alternative one can show that this is in fact the solution. Okay. So the general, you do not have a solution for this problem unless you have that there is this compatibility condition is satisfied. Now we can also study the Neumann problem for the general second order elliptic operator. So minus sigma ij equals 1 to n d by dxj aij du by dxi plus u equal to f, for instance, aij satisfying uniform ellipticity condition. And you can, so if you now write the corresponding weak formulation, so plus Neumann condition. Okay, so then what will be the condition? Find u in h1 of omega such that for all v in h1 of omega you have integral on omega sigma ij equals 1 to n aij du by dxj, sorry, is dxi and dxj, okay, and dv by dxi dx, plus now you will have integral on gamma, or rather minus integral on gamma aij du by dxj nu I d sigma and equal plus integral uv dx equals integral omega fv dx. So the correct natural boundary condition associated to this operator is d by d nu a of u, which is the definition is sigma ij equals 1 to n aij, so this is also sigma ij du by dxj nu I equal to 0, okay, and this is called the co-normal to the differential operator which is given above. Okay, fine. So this is about the Neumann problem. Now we can look at various other kinds of boundary value problems. We will see some of them in the exercises and so on. So you can have a Robin boundary condition, which is a combination of the Dirichlet and the boundary Neumann condition, which is equal to, so you get minus Laplacian u plus u equals f in omega. So what is the Robin condition? This will be u du by d nu plus alpha u equal to 0 on gamma alpha greater than 0. So this is called the Robin condition. Now you can also have the oblique derivative. You have namely du by d nu alpha 1 plus alpha 2 times d nu by d tau equal to 0 on gamma. So du by d tau will be derivative along a tangential direction in 2 dimensions. You have only one tangential direction. In higher dimensions you will have more than one, and therefore if tau is one of the unit tangent vectors at a point, so in that direction you can have. So this is called the oblique derivative problem. Okay, you can also have mixed boundary conditions. Okay, so for instance you have minus Laplacian u equals f in omega, u equal to 0 on gamma 1, and du by d nu equal to 0 on gamma 2, where gamma equals gamma 1 union gamma 2 and gamma 1 intersection gamma 2 is empty. Okay, so you have these things, and now in this case the weak formulation would be integral on omega, find u in v such that grad u grad v equal to integral on omega fv. Okay, where for every v in v, and what will be v is set of all v in h1 of omega such that v restricted to gamma 1 equal to 0. So you take the trace and then its restriction to gamma 1 should be equal to 0. If the n minus 1 dimensional surface measure of gamma 1 is strictly positive, then Poincare still holds. That's because you have essentially, what is this? If the first gradient is 0, then the function is a constant. But if it is 0 on a positive part of the boundary with positive surface measure, then the constant function has to be identically 0. So that is the idea. So Poincare still holds implies there exists a unique weak solution. And then if you can go and check that this condition we have imposed on the boundary, so the Dirichlet condition, which is essential condition, and if you work backwards with this bilinear form and write down explicitly the Green's formula and so on, then you should be able to show that a smooth solution, say H2, if f is in L2, and so f is in L2 and u is in H2 intersection B, then this will imply an weak solution. This will of course imply that du by d nu on gamma 2 will be equal to 0. Okay, so this you can now just check, it's very easy. So so now we will have a the next item on the agenda is to go and look at some other kinds of problems. So we've been looking at second order problems with various boundary conditions. So the next thing we will do is to look at the Dirichlet problem for the biharmonic operator, which is a fourth order differential operator.